Welcome to the 12th class meeting of the Introduction to DSP. We will have homework that will be posted today or tomorrow and will be due on next Tuesday. And we will have next Wednesday the first midterm exam. It covers up to Tuesday's class meeting material. And problems will be uploaded on the PLMS, similar way to the homework problems. So you need to bring your smart device or notebook computer to access the PLMS and also upload your solutions. Got it? And it's an open everything exam. However, you are not allowed to be assisted by a human being or LLM. So you cannot use LLM. Okay. Even though we are not yet finished chapter 3, today's main topic will be sampling, which is chapter 4. And this material will be included in the midterm exam. So you must be well prepared. There have been 2 messages from me. First one is that do not try to just remember some equations in the equation form. For example, in your signal gen systems, you had this. Sorry. This equality called the pathwise relation or pathwise theorem. But try to remember this way. Energy of the signal X computed in the time domain is the same as that computed in the frequency domain. Or, since this is the definition of the energy, signal energy is what? Is the energy spectrum integrated. Or if you want, signal energy is the same as the integration of the magnitude square of the Fourier transform of the signal, something like that. Okay, so the first message from me says, try to verbalize your mathematical results, not just in the form of equations. Second one is be careful about LLMs. They are very useful to have your outline 80% correct. However, at some critical moment, it gives you completely incorrect answers. So be careful. Okay, here goes the review of what we covered last time on Tuesday. I talked a lot about the basics of discrete time signal and signal filtering by DT-LTI system. So I derived not only the impulse response of a DT-LTI system, but also general impulse response of DT linear system. And then we cover the last part of the Z transforms, which is the use of Z transform to tackle a DT-LTI system analysis. So when DT-LTI system is described by a linear constant coefficient difference equation, then the use of Z transform sometimes, not always, sometimes greatly simplifies your effort, reduce your effort. So try to use the Z transform whenever you have enough time. So I repeatedly told you, try to derive the Fibonacci sequence, the general term formula, with 2 exponential functions. And then we move to the topic of filter design. And here, you have to remember this one. Suppose this is the set of all DT-LTI systems. Then There is a very, very small subset, but let me exaggerate the size. So here, LCCDE describes its input-output relation. As I told you, there are many important DT-LTI systems that does not allow exact description by LCCD with finite terms on the left-hand side and finite terms on the right-hand side. However, some non-describable DT-LTI system by an LCCD can be well approximated by a DT-LTI system describable by an LCCD. Actually, if the difference is not that large to our input signals of interest, then this approach using LCCDE is okay under certain tolerance level. So we focus on this small but could be very practically powerful subset of DT-LTI system design. Got it? Then what can we do? Sometimes we can totally circumvent computing this horrible infinite sum. As you see, this holds for all n, which means you need to compute how many times? Countably infinite times to have your value of y for every integer n. And at each time instant n, you need to sum up countably infinite product terms. So it may be horrible if these two signals are not very structured. However, when we can describe the system not just by the impulse response, but just by an LCCDE, then what can we do? We transform to the Z domain and compute this product of the Z transforms of the input signal and impulse response. If this allows a rational function of Z or equivalently Z inverse with careful choice of reason of convergence, then what can you do? Since this is a rational function, you have some constant A, constant B, and plot Z minus 0, I, Z minus 4, I from 1 to some M. Let me use J from 1 to some N, something like this. Of course, we usually want the highest order of the polynomial, the order of polynomial in the denominator greater than this one. If it is not, then we first apply long division so that we have something Z square, and some constant. Then we have something similar but less order in the numerator than the denominator. Then what can we do? We apply the partial fraction expansion, the 부분 분수 분해 in Korean. Then what? Then you recall these two important signals that has very simple Z transform with opposite reason of convergences. So you term by term convert back to the time domain, so you solve the problem. Got it? You do exactly what I told you, just what I said, to find the general term of the Fibonacci sequence. So try that. I emphasized more than 5 times, and you may expect that appearing in the exam. Okay. So if we restrict the interest to this small set, we have a very, very powerful tool with very, very useful Z transforms. But this is for kind of analysis, which means that you are given a system and find impulse response or find the output of the system when the input is something. Now, what about the design of a DTLTI system? In signal gen systems, you learned about Fourier transform, and it consists of 2 equations. First one was called, of course, the Fourier transform, but first one called analysis equation to find the Fourier transform. And second one was what? Your reconstruction formula from the Fourier transform to the original time signal. That was called synthesis equation. What is synthesis? In Korean, it is called 합성, but you may say that it's analysis and design. So from frequency domain, you design something that has some time, this time domain description. Similar. Here, we talked about the analysis of a DTLTI system, but we want to design a DTLTI system. The problem is that sometimes our desirable DTLTI system may be here. Then what do? As I told you, we approximate. Sometimes, even though it is here, it could be very easy to design. However, if we design something that closely approximates the system, it could be okay. So the almost entire filter design problems in digital signal processing textbook and graduate level textbook and even other digital circuit theory book for filter design, they just use Z transforms. What does that mean? They consider linear constant coefficient difference equation to design a DTLTI system. Then what do you need to choose? So let me recall you what was the LCCDE. So you had, AK, and you had BL, theoretically for all n in the set of the integers. So here, what are the design parameters? So what should be determined to completely describe the difference equation? First, order. How many current and past inputs you are going to use? And this one. So outputs. How many current and past inputs you are going to use? By the way, even though we set k equals 0, L equals 0 as the lower limit, if your system is not necessary to be causal, which means that if you can use future values in some sense, then you can choose some negative values here and there. Got it? In that case, actually, your current time may not be physically current time, but your convenient choice as the origin of the time index. Or even though we call this is a difference equation and n is the time index, n could be spatial index or something else. In that case, it may be okay to use some future values. So even though I'm saying the lower limits are zeros, you shouldn't be too restricted to that. But anyway, let's focus on that. So You have to choose M, you have to choose N, and what else? Of course, the constant coefficients, right? You may say that, okay, anyway, M plus 1 coefficients you need to choose on the left-hand side, and N plus 1 coefficients you are going to choose. So actually, what you need to choose are M plus N plus 2 parameters. Got it? An interesting thing is that there is a theorem, not well-known theorem, similar to Weierstrass theorem. And unfortunately, Weierstrass, I don't exactly remember the spelling of his name, but probably correct. And he was so good a mathematician and had a lot of Weierstrass theorem. One of the Weierstrass famous theorem was like this. Probably you've seen something similar. Suppose you have a real function that is continuous on the interval a to b, finite. So it's a continuous function. Got it? Then this is the function f. Then it can be approximated by, x to the k, x raised to the power of k, mth order polynomial, arbitrarily closely. So it's very interesting. So you can approximate any function, any continuous function, using a polynomial. And you may say that, is it really true? The trick is here. If the signal varies very fast, you need very, very large number m. Got it? Now, similar to this idea, there is another theorem. I forgot the name of the inventor of the theorem, but there is something like this. If you have a signal, continuous, that is continuous, then so by choosing some value capital M, N, AK, and B else, you can arbitrarily closely approximate a continuous signal. Got it? So they are very similar, and you can immediately notice that actually this is a subset of that theorem, because if you choose the denominator as constant, then they are the same theorem. So what's the implication of this theorem, even though we do not prove? The story is like this. Suppose you have some Z transform of a DTLTI system. So it's like you have a system function. Now, this can be well approximated by something like this. Got it? After some manipulation. So here goes the idea. Whatever DTL-type system you want to design, let's just forget about general design tool, but to use LCCDE, because LCCDE, linear constant coefficient difference equation, always gives you the G transform in the form of a rational function in Z inverse or Z. Got it? That is the idea. So you want to design a DTFT filter. There could be many approaches, but there is one very simple approach to use Z transform. Let's restrict our interest to DTFT system whose input-output can be, this relation can be describable by an LCCD. So you just need to now choose what? M, N, and coefficients. That's all. Got it? And this is the way we design most of the DT-LTI systems. Got it? Unfortunately, this story, you may say that, hey, obvious, professor just talks the same thing again and again. Unfortunately, if you look at our textbook, and if you look at other textbooks, surprisingly, not many authors of the textbooks writes what I just told you. They just talk about, okay, here is basic filter analysis using G transform. Notch filters are described by this one, and blah, 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 blah. Got it? So never do that. Some of you may become a professor in electrical engineering and may teach DSP in 10 years. Please emphasize what I just told you to your students. Got it? By drawing the Venn diagram. So sometimes we restrict ourselves and have very high creativity. So there goes some proverb says, think outside the box, something like that, right? So in Korean, 경계를 벗어나서 생각하라, 박스 밖에서 생각하라. But unfortunately, when Soviet Union's old Russian communists analyzed great inventions, one of the things they have found is that creativity sometimes springs out when you have very high restriction. So create inside the box. So you put a lot of restrictions and then do something extreme. So that's what's going on here. We restrict ourselves to use Z transform, LCCDE together, and design a linear system. What can we do? So that's the idea. First, as in the last class meeting, at the end of the class meeting, as I told you, digital filters are similar to analog continuous time filters in the sense that many of the filters, their properties are described in the frequency domain. So for example, suppose this is the omega axis and you have origin and this is pi. And this is negative pi. And suppose this is the frequency response over DT-LTI system. And if it looks like this, then what do we call? We call this as a ideal low-pass filter. What if we have something like this? High-pass filter. What if we have something like this? Band-pass filter. You know this, right? Be careful, even though I didn't repeat these DT Fourier transforms are periodic with period 2 pi, so you have to kind of copy this part, this one period of the signal, and what? copy and paste, 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 so that you have infinite replicas, so that you have periodic signals. So as I told you, of course, not every filters, their properties are described in the frequency domain, but many important digital filters are kind of named in by following their frequency domain characteristic. So what you want to design is what? What you want to design is actually this one. This is what we want to design. Now, we are going to use the Z transform. How? The link between Z transform and DT Fourier transform is what? The DT Fourier transform can be seen as the Z transform evaluated on the unit circle. Got it? So even though we design the system function, capital H of Z, we are going to evaluate that function only on this unit circle. So if we have the third axis that represents the magnitude square of the Z transform, for example, this axis means this one is it's coming from the plane anyway, then we have some function, right? Then we use our knife and we slice out the other things, and then we have some kind of cake, wedding cake type thing, and we see what? We see the shape of the edges. Then what happens? Right? So I look this height and draw, then what do we have? Periodic signal, because we have circular something. Got it? So this is the idea. Our desired property is probably the variation of the height of this cake at the edge, the cutting side. But we design the Z transform so that this is well approximated to the desired property. Now let's focus on our first example, notch filter. What does that by notch filter? Notch filter is a very special type of band stop filter. What is a band stop filter? Band stop filter is that you choose some band, say here to here. Then what you want is that you have the magnitude response, for example, looks like this. This is a band stop filter. And notch filter is an extreme version of band stop filter. You have very, 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 very narrow stop band. So ideally, you may have something like this, but if you design, then we have some smooth functions, so probably if they look like that, right? So notch filter has response something like this. And here you have some negative omega 0 and positive omega 0, representing your frequency, radian frequency or angular frequency, to be cut out or cut off. This is the notch filter, and we want usually the height, non-zero part, as equal as possible, like the ideal band stop filter. But sometimes we have transition area. Now here goes one possible way to design a notch filter that has notch frequency omega 0. Take a look at this one. See that? It's what? Z transform, system function of our proposed notch filter. I'm not saying this is the only possible notch filter. This could be the simplest notch filter. One of the reasons why I say simplest is that the numerator is order 2, and the numerator is order 2 and denominator is order 2. So if you rearrange that one so that you have linear constant coefficient difference equation, then how many current and past values of output and how many current and past values of input signal are used? 3 and 3. Because if you expand this one and somehow rearrange, then since this and that are conjugate pairs, you have just real coefficients and second order polynomial. And here again, even after you divide the numerator and denominator with z square, so that you have some constant plus some constant times z inverse plus constant times z negative raised to the power of negative 2, right? Because in your use of z transform, you use z inverse, not z. So we intentionally divide the numerator and denominator by the highest order z. Got it? So this could be the simplest. And since this is given, not yet I asked you, hey, design notch filter, but this is a way to use Z transform design a notch filter. Let's try to plot our pole 0 plot. Then what happens? First, what are the poles? Poles are the roots of the denominator polynomial. And we have r times e to the j omega 0 and r times e to the negative j omega 0. So if r is less than 1, and you will see why we choose some real number less than 1, but here is first pole, and here is the second pole. By the way, the distance is r less than 1, and angle is omega 0 and negative omega 0. Got it? And now, where are the zeros? 1 times e to the j. So suppose this dashed line represents the unit circle, then here is your 0, and there is another 0. And we have some filter gain, capital G. It could be some number, non-zero. Now, are we done? No. We are not just interested in this Z transform, the system function of the DTFT system, but the Z transform, the system function evaluated on this unit circle. So we are going to, it's like we have a very large oven. We baked some cake, and then you have a knife and cut this center part out. And now on the plate, you have this center part, and take a look at, okay, omega 0, something like that. Now, when you rotate by omega 0, what will happen? Here is a 0. What does that mean? If this axis means this axis means system function absolute value squared, then what will happen? You have some continuous function, right? But since this is 0, what happens? This surface touches the plate here and there. So when you cut them out and see what happens, when you see omega 0, suddenly the cake drops to the plate and spring up, right? And plunges and going up, plunges going up. Now, what about this R? How do you choose the value of R? Whenever you have this kind of situation, you need to become an extremist. What does that mean by Korean? 극단주의자. So you consider two extreme cases. What? R close to 0 and R very, very close to 1. So let's consider R very close to 1 but less than 1, which means that this is very close to that one. And pole means that, as you have seen in signal-gen systems about the Laplace transform, pole of a rational function really makes us to have an analogy that we have a pole and some elastic surface. So it's like here we have a pole that makes this magnitude scale value very, very, very large and actually goes to infinity, right? However, here you nail down with hammers of this surface. So around here, what happens? If you just see entire Z, here the value is very large and goes to infinity and then suddenly goes down to 0, right? If it is very close to 1. But the fact does not change that at omega 0, it's 0, right? Because we have a 0. Now, what about we are rotating, we are working on this line. Suppose we are here. Here, what happens? If these are very close together, means R is very close to 1, what will happen? From my point of view, this value, that value is what? In terms of magnitude, almost the same, right? See that? See that? If this is some e to the j omega 1, then what does this mean? Distance from here to there, and distance from here to there. And if they are very close, distance is almost the same. And if you take the magnitude scale, then they almost cancel and becomes 1. Got it? So here some non-omega 0, omega 1, its height, this part is almost 1. If R is very close to 1. Got it? However, if it is not or, even though this is very close, your omega 1 is not close to omega 0, what will happen? This distance could be shorter than that one, so you have some non-unity value. Got it? So this is the idea. So if R is close to 1, and of course less than 1, then you have very sharp notching. And if it is not, then you have some smooth value. Got it? And you may say that, hey, then it's obviously good to choose that one over that. The problem is that what is the criterion for Bibo stability? Bounded input, bounded output criterion is translated to what? In terms of impulse response. Absolute summability. And that is actually, interestingly, what? The necessary and sufficient condition for DT Fourier transform to exist. we are handling DT Fourier transform of the filter impulse response. Now, if R is very close to, so pole is very close to 0, and we have production variation, what may happen? This could be very close to here, and maybe generating some numerical instability or problem. Got it? So even though that is not deeply discussed here in this part of the lecture, you always think in this way. Hey, we have a mathematical model. If this mathematical model is perfect, exactly implementable in the reality, what is the best choice? R less than 1, but infinitely close to 1. That could be the good choice. However, in reality, what could happen? Especially when we use finite number of bits to describe the coefficient values, we may have problem. It's like you made this R very close to that one, but you are some circuit theory friend designing real system, say, hey, okay, I have only 8 bits, and okay, they are the same, 1. Then suddenly your system does not work. Got it? So let me repeat. This is very important. Even though we are learning mathematical modeling and what kind of mathematical property we can exploit and we can enjoy, implementing that one in the real world may give us a lot of headache. So be careful. Got it? Anyway, so we've seen one approach, one example. And here, as you see, that you have y, 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 and x, x, and x. Got it? You should be able to convert that z transform in the form of a rational function of z into that linear constant coefficient difference equation. MATLAB example will be skipped. Here goes another filter, second one. And this filter is named all-pass filter with sometimes without this dash. Some people love to put, some people does not. What does that mean by all-pass? What should be? All-pass, okay, band pass, low pass, high pass, band stop. All-pass? Strange. That was my feeling when I first saw this one. So I thought this filter, hey, everything comes out here. And since this is the impulse response, what is the z transform? 1 for all z, right? Hey, I have an all-pass filter. Of course, the all-pass filter is not just this one. You can include this one as a special case of all-pass filter if you want, but this is not what you want to say. All-pass filter, since this is a kind of filter, has the property like this. Its magnitude response, or magnitude scale, equals 1 or constant, just let me say 1 for all omega. So the property of this all-pass filter is described in the frequency domain in terms of not just the frequency response, but just the magnitude response. Got it? What does that mean? You may have some strange angle or phase response. It's not necessarily constant or linear function of omega. By the way, if it is a linear function of omega, what can we say? It's a delay system, right? For example, if this is delta of n minus n0, what do you have? This equals e to the negative j omega 0. Sorry, omega n0. Right? So magnitude is 1 and phase is linear function. We are not necessarily talk about this. Okay? Not this. Not necessarily constant or linear function. It could be arbitrary as far as this is okay. Got it? So we want to design a filter whose magnitude response is constant for all omega. That's it. Now, what would be the simplest one? Think about the answer for 5 seconds. 4, 3, 2, 1, 0. So this is the problem, actually, the limitation of modern education. And long ago, around 100 years ago, there were so-called, how do they say that? The private tutors living in your home, teaching almost every class, every course to you, even from riding a horse to fencing, something like that. Probably you've seen in the movies describing late 19th century. And you may probably wondered, hey, they are low paid, right? Even without family, because they are living inside the billionaire's house, right? And usually very old compared to relatively at that time, probably mid-40s and 50s. Strange, right? How they could be a very good teacher. They are not like, who is the name? 현우진? Okay, they are not 현우진, right? Even 현우진 cannot teach you riding horse very good. Strange. The importance of private tutor or house tutor is that they know when to stop. So for example, I'm your servant and teaching DSP. So you are 도련님들 and 아가씨들, for example, in some aristocrat, 귀족. Got it? Then I would say that, okay, let's stop here and think about what could be the simplest form of all-pass filter in terms of the system function, which means the Z transform. And you may say that, well, I don't know. Okay, I will give you 2 weeks. In the meantime, let's have a ride of our horses. And you choose one of 12 horses, right? That's the problem of so-called mass production education. So I'm very sorry. Yeah. But since I'm recording this one, probably in some future, in 1 year later, some students will view this one and probably I'm asked them to, hey, this is a flipped learning course on DSP. You watch 2025, my lecture, and come and take the quiz immediately and do some MATLAB programming in order to have lunch as quickly as possible. So you watch this video in the previous day and stop here and think as your time allows. 30 minutes, 40 minutes, 1 hour, or 7 hours before you go to the classroom. It's very unfortunate that I have to just give the answer, like some injection education, 주입식 교육. I'm sorry. The basic idea is this one. You use this form of Z transform. Now, can you see the corresponding linear constant coefficient difference equation? The trouble is that you may say this, hey, professor, something's wrong. See that? It seems P could be a complex valued, right? In that sense, this is not yet good because we usually think about real coefficient constant coefficient, linear, real constant coefficient difference equation. In that sense, this is not yet complete, but converting this one, making this one more complicated, but to have all real valued coefficients is not that difficult. You can just think about the solution in a few minutes. So let's just focus on this one. Even though this filter may not be just implemented two-term real valued LCCDE. It is now complex valued LCCDE. But anyway, so what is this? So let's consider pole zero plot. So here goes the pole if P has magnitude less than 1. And you know why we choose that? Because we want our system causal. Why? We want to implement in real time. Then what happens? When we use this Z transform, we are going to use exponential functions, right-sided. Then our reason of convergence looks like some circle outside. So largest magnitude poles you have, then outside of them should be reason of convergence. And in order to have Fourier transform, because your filter characteristic is in terms of Fourier transform, your unit circle must be included in this reason of convergence. So your pole must be right inside the unit circle. So I'm assuming P has magnitude less than 1, similar to our Notch filter design. It seems that we cannot go to the next chapter. We just have 25 minutes. Anyway, let me be quick. So anyway, so here is the pole, P. Where is the 0? And 0 is located 1 over P conjugate. And what is the magnitude of 1 over P conjugate? 1 over magnitude of P. So if the magnitude of P is less than 1, its inverse is larger than 1. What about its angle or phase? Interestingly, here, if P has representation like R e to the j theta, then what about P conjugate, P inverse? 1 over R e to the negative j theta. What about 1 over P conjugate? This is real. Now it's changed. So P and 1 over P conjugate have the same phase. What does that mean? When you plot pole 0 diagram, you have a pole here, then you draw a straight line crossing the origin. Then here, from the distance 1 over magnitude of P, you have 1 over P conjugate. Does it look like something similar to the Notch filter case? It's similar. The difference is that in Notch filter design, we intentionally put our zeros on the unit circle. Now, the zeros are not on the unit circles. Right? Here, of course, there is single zero, but we have the other term so that we have second order LCCDE with real valued coefficients. You can do that. So now, consider the magnitude square of the system function, this axis. Then you have to consider entire complex value z. Then around here, what happens? This is a pole. So you have very large number. And if you move that one, what happens? Suddenly it drops to 0, right? So you have such Z transform magnitude scale. But we are not interested in that. We are interested only on the Z, H of Z magnitude scale on this unit circle. So again, you take out your cake knife and cut the inside out and put it on your plate, and you see what happens. That is actually the same as you evaluate here, e to the j something. So you plug this here and there and take the magnitude square and see what happens. And amazingly, see that instead of theta, let's say omega for all omega. So you replace z with e to the j omega, and you carefully compute the magnitude or magnitude square. What will happen? And it's not that difficult because all the information you need to reach the solution answer is here. You do it yourself, and amazingly, you have this. The magnitude square of the system function evaluated on the unit circle is constant for all omega. Got it? So we have reached our desired goal, all paths property in the frequency domain, by placing pole and zero where? On the single straight line crossing the origin. And pole is located inside the unit circle, and zero is outside the unit circle, and their magnitudes are reciprocals. And here goes the definition you need to remember, even though our book does not have it. A complex number, z, given a complex number, z, 1 over z conjugate is called conjugate reciprocal of z. By the way, what is reciprocal? If you have a real number, r, the reciprocal is 1 over r. So you have z, what is reciprocal? 1 over z, but here you have conjugate. Ready? So a complex number z and its conjugate reciprocal has what? Here goes the, it's too simple, but let's say lemma. Angle of z equals angle of its conjugate reciprocal. Ready? As we've just seen. We use this property and some others to design a filter. Of course, as I told you, if P is not chosen as a real number, then your first order, two-term LCCDE must have a complex number. So you need to have a three-term LCCDE, but anyway, you can do that. Okay. Here was another example. This is the last example. And suppose you have this filter whose input-output described by an LCCD. So even though you have two terms here and two terms here, be careful. This is what? Second order delay, -2. So if you move left side, how many terms? 3 terms with 1 0 coefficient. And here you have the current input and 1 first order delay. Now, you z-transform the LCCDE to have this single rational function in z. And as I told you, you have the second order term in the denominator and first order term in the numerator of z inverse. Now, you know how to find the root of the denominator. As I told you, you learned high school math to become an electrical engineering undergraduate student. So you can find 2 roots and rewrite them like this. Am I right? So you multiply and confirm that. And you may say that, wow, something's wrong. You do what, actually? From here, you multiply what? Z squared to the numerator and denominator, assuming z is not 0. And that's actually correct because we are going to choose reason of convergence outside the unit circle. Outside some circle that includes unit circle, but possibly not including origin. So z shouldn't be 0. In that case, you have z squared plus 1/2 in the denominator. And in the numerator, what do you have? Z squared plus z. That is why you have this. Got it? So it's like usually LCCDE, because it has delay components, involves z inverse squared cubed, something like that. So when you just by inspection from the system function, you have rational function in z inverse. In order to plot the pole zero plot, you somehow convert them as what? Rational function in z. Got it? Is it clear? Then you place X marks and circle marks. So here goes X, X, and circle, circle. Now, we designed this one in some reason, designed this one. We have chosen the order and coefficients by some reason. But anyway, we are going to view this as a filter whose characteristic is described in the frequency domain. Then what is the next thing we need to do? Consider an axis, what? Magnitude square of the system function. Now, here, actually, there is no pole, right? Because it's at 0. So your rubber plate, you have a nail. So it starts from here. If you walk through 0 to there, then 0 and some value and 0 again, right? Because there are two zeros. What about you move that way? 0 and suddenly goes to infinity. And if you somehow move back, goes down and probably some non-zero value, right? That's why I plotted this one. So if you move that way, however, we are not moving only this way because we are going to move on this unit circle. Then what will happen? Here, so we walk along this one, and this is omega. We know that at pi over 2, we could have very high value depending how close the pole is to the unit circle. If it is very close, then our pole, infinite pole, is very close to the unit circle. So when we go work here, this value could be very large, not infinity. So something like this, right? Since there is no 0 here, okay, something like this. What about at pi and negative pi? We have 0 here. So it goes down and down. So the magnitude response or magnitude square response of this filter described by this LCCDE may look like that. Got it? And that was kind of some resonance system at frequency these two. Got it? Okay, so we have just exposed a little bit about the DTFT filter design by using the Z transform, and we will be back after we do some other important things like sampling and DFT and other things. You see that here goes the LTI analysis and structure that is related to the design again. But anyway, so we move to chapter 4. Chapter 4, as the title says, is all about sampling. Right? And sampling is one of the way to construct a DT signal and also sometimes DT system. Be careful. Last time I emphasized this one. Not every signal modeled as a DT signal is obtained by periodically or uniformly sampling a CT signal. So this is what I told you in the last class meeting. And never forget this. Got it? Because, as I told you, too many textbooks. Somehow, they are not explicitly saying that the inverse is true, but they have very, very misleading sentences saying something like every signal is obtained by sampling. No. Okay? Not every signal modeled as a DT signal is obtained by periodic sampling. However, still, sampling is a very important method to obtain a discrete time signal. By the way, you have already had an experience of processing stock market numbers, signals from the Excel file I've given you, right? And if you remember still, the Excel file was obtained by sampling the stock market indices like Kospi or some specific companies value at every 5 seconds. Why did I do that? Then what could be the most complete description? Consider that. Suppose here is a stock market and no other people. So we are the Korean stock market and you are the players. Got it? So we have around 8 persons. And I'm the broker or operator. So some of you have the Samsung Electronics stock. And the others of you want to buy. And the owners want to sell or buy more. What will happen? You give me your intention to buy or sell how many stocks at some price. And what I do is that if your sell order finds less price than your buy order, I match 2 of you so that you can buy and sell. Then what will happen at some point? At some part, there are, for example, those who want to sell the Samsung Electronics stock at, for example, 1,000 Korean won. And some people want to buy at 900 Korean won, right? 900,000. Usually they quantize the prices, like 1,000 won or 51 or 5 won, something like that. Now, what will happen? If no one give me a new order to buy or sell at lower price, sell lower price or buy higher price, no trade occurs. So one of you changes your mind. Hey, it seems that I cannot sell at this price. But you see that there are some others of you who want to buy your stock at 900. So you change your mind and submit the sell order to me. Hey, I will sell at 900. Then what will happen? If that time is 310, at 310, we have our transaction. Now consider you are very, very fast. You work in microseconds. What will happen? There could be a lot of trades, right? But they are not periodically occurring. Now, we have a lot of trades, but I can only record at every 5 seconds. What will happen? Probably I will combine all the transactions for the rest of 5 seconds and record them in my Excel file. Actually, that is what occurred in my Excel file. Got it? So that Excel file does not include every trade, actually. It's kind of sampled version. So from here, at time hour 0 second for our convenient choice, and 5 seconds, actually, they have changed the price a lot of times in milliseconds. And suddenly I sample and record and saying that, okay, Samsung Electronics stock just has risen for last 5 seconds, 101. Actually, it changed a lot. Got it? So sampling is sometimes very misleading. That's what I want to say from this example. However, it is necessary because we want to record some history of stock market. But we cannot record everything because there are around 40 million investors, and you may say, we have population 40 million. Actually, there are some machines they sell and buy stocks, right? So more than probably 40 million players, and they may send orders through internet at different time. It's almost impossible to completely record the thing. Of course, even at the brokers, 증권회사, brokers computer, they may process the transaction at every, for example, 10 milliseconds after accumulating all the orders, because they can never have infinitely fast computer anyway, and infinitely fast Ethernet switches anyway, but I don't know. Got it? By the way, this is one of the idea of so-called high frequency trading. So you purchase very, very fast communication line, optical from, for example, or sometimes microwave. And then you have a very, very, very fast machine. And you observe the price variation, and you find that some people say that I will sell the Samsung Electronics stock at 900. And you find that some people want to buy this one at 1,000, but this trade is not yet made, but I've noticed. How can I earn money? I buy at 9 and sell at 1,000 within a fraction of seconds, not just fraction of milliseconds. That is high frequency trading. And it was not that possible in Korea, but that is one of the way occurring in US stock market. Of course, that made a lot of trouble, so the stock market operators somehow try to ban the too fast high frequency trading. But now something interesting happened in Korean stock market. Before, we had only one stock market called KRX. And as some of you know, now we have ATS, the second stock market. And they sell almost the same stocks, but they receive orders differently. So if you watch the prices of two different stock markets, sometimes you find that a guy wants to sell Samsung Electronics stock at 900, and some guy wants to buy at 1,000, and you spot that and purchase this one and sell to this guy, getting 101. And you may say, hey, Professor, 100 Korean won. Not just a single stock, maybe 1 million stocks, for example. Then what happens? 1 million stock at 900, 1 million stock at 1,000, and you just have enough money and purchase that and sell that. How much do you earn? 100 million Korean won. Sorry, not 100 million. Is it 100 million? Yeah. 1억 won, right? That could be possible, but I don't know. I don't have that such a machine. Anyway, so we've just started to talk about sampling. And on next Tuesday, I will talk more. And that part will appear on your Wednesday exam. By the way, you may not have enough time to understand what I will say on Tuesday and solve those related problems. But about sampling, you should have been exposed in your signal gen systems course. So please, please, please try to find the materials available from the web or from your old textbook about sampling. And try to understand that not only in the time domain, but also in the frequency domain. I will cover this part very fast and put some problems in the midterm. Okay, that's all for today.